So this talk, just to give you expectations of what will be in this, I'm going to talk about 7 almost completely different things, all kind of software motivated or software oriented, code oriented. And all of these things, as the title alludes to, kind of come from my own work. I mean, I don't develop software just to develop software. I'm trying to understand the brain, and part of that is a very data and code heavy approach. And so over the past 15 years, I guess, I've developed a lot of software. Okay, so just a brief introduction about where I'm coming from. As Amanda mentioned, I'm at the University of Minnesota. I've been there about a little over a year now at the MRI Center there. I don't know if you are aware of this place. They specialize in high field MRI research, engineering, and so forth. So just in a nutshell, what I work on, although most of this talk is not really about this, it's work on using fMRI specifically to develop what I characterize in a phrase, computational models of how visual processing works in the human brain, and specifically in the area of like form vision. So this would cover things like face recognition or word recognition. I'd be more than happy to talk, offline about what this actually means and all the various details that are involved, but that's not what this talk is about. Okay, so just and briefly about the approach, which I've already somewhat alluded to. I kind of divide it into 3 different components. One is understanding what type of experiments to do, so there's a lot of important experimental design, and of course a lot of details of how to effectively use fMRI, which is a very advanced technology, and we could spend a whole semester talking about all the details of MRI physics and imaging and so forth. So there's a lot of expertise there, especially if you want really high quality data. And so I study vision, and in vision there's a rich theoretical framework of how we think vision works and the complexity of vision. A lot of our brain is dedicated to vision, so there's a lot of, theoretical backing in what I do. And then the last bit is, since I do take a kind of data-driven approach, there's a lot of details on doing appropriate statistical and data analysis to your data, and that involves a lot of programming, which I presume is relevant to what this brain hack is about. Okay, and if you're interested in anything in this talk, a lot of resources are on the lab website that I've made, so you can just go there right now or after the talk. Okay, so that's just kind of a big picture, and just to cast it in terms of what you just heard, since it's probably fresh in your head, connectivity is kind of a new way to think about brain activity and interpreting it, and then I guess all of these studies are very much the task-based approach. So a task in a very broad sense of there's an explicit experiment, you have the subject do your experiment. It doesn't have to be vision, it can be some more cognitive thing, and we try to look at the data and try to figure out what does the physiology of the brain tell us about what the brain is doing with that experiment, with the task that you set in front of the subject. Okay, so just a little bit about how I think about computation. This probably applies to most people here, especially if you deal with fMRI. And so what we have done is to steal bits and tools from various software packages as we see fit. And then in my case, I use MATLAB. So we sort of integrate all these tools and write our own MATLAB code to kind of build a whole pipeline, so to speak, to analyze the data. Some of the things I've developed make sense as a standalone tool, and here are just 2 of them. And they're kind of a self-contained package that you can go read about. And in, I guess, the data sets I work on, they tend to be memory intensive, so it makes sense to do this on large workstations with a lot of memory. And in some cases, you want to analyze individual voxels at a time, for example, for some costly nonlinear optimization techniques. And in that case, you can farm out these analyses to clusters of computers which can operate on single voxels at a time, just to speed things up. Okay, and code-wise, there's the link to the GitHub, a collection of repositories I have online. Okay, so that's kind of the broad picture, and as I mentioned, now we're going to see 7 somewhat unrelated topics, and a lot of this is mainly just to gauge your interest, and if you want to talk more about it, I'd be more than happy to tell you the details. These aren't like specific project proposals, but more like here are various things that I've done, and any number of them could be extended, or we could talk about what might be useful to work on. So random topic 1 of 7, automated surface visualization. So cortical surface representations, I'm sure that's familiar to you. We're talking about fMRI data. And one thing that we've dealt with somewhat recently is the need to do this at high volume. Basically, when we have, as Amanda alluded to, we're investigating high resolution data, and we're actually trying to do a lot of anatomical understanding and understanding the small spatial. Anyway, there's a lot of data to look at, and we need something really fast to just generate massive numbers of these figures so we can pour through them quickly on all our subjects and all different views of the brain and so forth. And so it needs to be automated, needs to avoid any manual intervention. And so that was the requirements that we were faced with. Of course, customization is really important. So we have all these ways of what color map to use, how to transparent overlays, blah, blah, blah. And we do use free servers. So there's some sort of dependence of the way we've structured the code currently on having some incarnation of free server having been run, but of course with additional work we could generalize it to work with whatever package you prefer. And I'll show you a couple images about this high resolution stuff. So we do modify free server a little bit, or at least call various utility functions in free server to deal with really high spatial resolution data. And just a little bit about a method, since I think precision is really important to at least what we want to do. And the mechanism here at the core is really simple. Everything's treated as an image. Images are made of pixels, and each pixel is mapped to the nearest surface vertex using the nearest neighbor. So there's no explicit smoothing going on, and we can generate these nearest neighbor projections at any resolution we want. And a little bit on mechanics. As I mentioned, we have a need to generate many of these, so we use caching. I mean, this is simply an indexing operation that you can just cache away, and indexing is very fast to operate, so then you can generate maps really quickly. Anyway, so here are some little pictures, eye candy. Just to orient ourselves, this is pretty typical. We have many different views. We might want a view of the brain. One's flattened, but induces distortion, and then these other views. Depending on which brain area you're interested, you might want to see a occipital view or medial view, etc. The colors are just an atlas taken from Sabine Kastner's probabilistic visual area topographic atlas. Anyway, so this just gets our feet wet thinking about these things. And you might imagine you might have 20 or 30 different views you need to see, because it's nice to see the whole brain in a single image, but it is very hard to orient yourself anatomically. So you may need these inflated views, and if you have inflated views, you can't see the whole brain at once, so that means you have to have 5, 10, 15 different views, and that's a lot of different visualizations, and we need methods, I think, or our lab needs ways to quickly generate these that have no GUI intervention. So here's just a sampling of the details don't matter. Obviously, we can paint whatever values we want. Basically, any data set where values are associated with vertices of some 3D mesh, we can visualize, of course, using different color maps and different different labeling schemes and so forth. So we easily have like thousands of these for a single subject, and then we have multiple subjects. And even these images, these PNG images, take a lot of disk space, let alone time pouring through all of these images. So here are some more examples. This is just a ventral view of the inflated surface. What's being plotted here isn't that important. It's an anatomical computation, which is highly affected by soul-side gyri organization, hence it looks like that type of map. And this is, the reason I put this here is just to show you kind of the high-res aspect of this. So these are actually densified meshes, so the inter-vertex spacing is, it varies depending on the folding of the brain, but as low as 0.3 millimeters or so. And so this quantity being visualized is actually potentially varying for every vertex, and if you zoom in, you can see the nearest neighbor operation, so that you can see that this, whenever you see a color change, is presumably because it's being influenced by a different vertex of this preparation of the data. Here's another example. This actually gets into cortical layers. As Amanda mentioned, we're exploring cortical layers, as are other groups. And what you're actually looking at here is just raw T2 star susceptibility data. So it's like the raw EPI data, assuming you're using EPI to measure functional measurements. And what we're going to do is just show a little movie of the data sampled from deep to superficial. So as you can see, this is just the mean intensity of your functional volume, and there's a massive change as you sample from deep going more superficially. And if you know anything about the nature of fMRI data, you might suspect, or you might know what this is. This is basically the effect of veins on your data. And so this is the same thing, just in an inflated view, just so it looks more reasonable. And you can see as we sample from deep to superficial, you see this massive effect in the data. And this is high-res data. And I'll show you a couple of slides later what it looks like at lower resolution. But you might imagine, you might be wondering what's going on? What does this do to our fMRI data? And that's actually a large component of what we're grappling with. And it's not an easy thing to figure out. Okay, so that's, these are just more examples of visualizations. What is this? Oh, this is a pretty picture or a movie. So this is a zoomed in view of a kind of a flattened representation, and it went really quickly, so I will replay this for you. We see 6 different panes corresponding to different cortical sampling, depth samplings. And this movie it's really just a movie of activation. So after multiple trials, you estimate your finite impulse response model. It's really just a time-locked average of the response to a stimulus. And what you're going to see in this movie, again, the details don't matter, but you might imagine it's visualizing over time. Of course, time is slow in the case of fMRI. The evoked responses by different stimuli. The colors represent different preferred stimuli. And if you look carefully, there's an interesting feature of it that you can, I'm going to play it now. Oops, no, I'm going to try to play it now. Okay, I'm going to play it. Let's see if this works. At least you can see at a gross level, there are some differences in the time course across cortical regions. Anyway, this is just an example of a way to use these visualizations. You can compile a movie out of them. Okay, so that was random topic number 1, which conceptually is related to random topic number 2, which is brain art. So it turns out in generating a lot of these visualizations, the goal was to figure out something about brain or methods, and a lot of it actually looks pretty visually pleasing or interesting. So I'm just going to show you some examples. I won't spend time telling you what the data actually are here, but you can just derive visual pleasure from these maps, maybe. This is very pixelated. Of course, we could generate a finer grained representation. I will comment on this one. I like this one because this is, I don't know if you can tell from the image contrast, but anyone have any guess what type of data this is? It's actually a mistake. It's like a T2 weighted volume that's been misregistered and basically randomly plopped down on a cortical surface that's then been inflated or sphericized or flattened. And so you can actually see gray-white tissue contrast that's been misregistered down hereabouts. That's I guess this is white matter and this is gray matter. Anyway, so you incorrectly project this convoluted, T2 tissue contrast onto the cortical surface, and then you visualize it, and it actually looks very interesting. But it is a mistake. This is that susceptibility, just raw data that you saw earlier. Not so important. And this is also a mistake, but it's visually interesting. And this last one actually, well, it's correct and it serves a useful purpose. So often in visual studies and probably other studies of other parts of the brain, you don't get full brain coverage. And so being very careful about how much coverage you're getting and how that intersects the convoluted cortical surface is really difficult to see. And so we need visualizations of slice coverage, basically. Anyway, oh, and for fun, I printed these out on canvases, and they kind of look pretty. Okay, so random topic number 3, high-res fMRI preprocessing. So I've already alluded to this, but now I'm going to give you some amount of detail of how we think about that. This is code. It's not super generalizable yet. It could be worked on. But here's our kind of approach. So we get a bunch of T1s on people just because we need to do this with high precision, and if we can simply just gather more data and average data to improve quality, that's great. So we do some co-registration of T1s, averaging to improve SNR. So that co-registration is a big part of fMRI data, as you're probably aware. So there's a bunch of co-registrations we think about. So we do a bunch of within modality T1 to T1 co-registration for a given subject, and also T2 to T2. And then we do a T2 to T1 registration step. Of course, different tissue contrast. There's some potential pitfalls there. It's always important to visualize and check for accuracy. And there's also our functional data to the T2. So these are similar in tissue contrast, so that's a little more well-behaved. And so there's a bunch of co-registration in our pre-processing. As I've already mentioned, we're using FreeSurfer's ability to do a pretty good job automatically giving you segmentations and surface reconstructions. We do perform additional steps to that to make these surfaces even denser, because the high-res fMRI data that we're talking about is 0.8 millimeter nominally, so 0.8 millimeter isotropic. So that's the standard FreeSurfer meshes, I believe, have inter-vertex spacing of 1.25 on average. So the functional data is even below that. So we have to do something, otherwise we're going to lose some of the resolution in the original functional data. And then make layers, and then these surfaces get huge, so we got to truncate the surfaces. We don't get coverage beyond the posterior half of the brain, so it just makes sense to save on memory requirements just by truncating these things. So in terms of the functional pre-processing, we get standard field maps with 2 echo times. There are some details I believe are important in how you regularize these things to use the field maps to correct for spatial distortion. I could talk more about that ad nauseum. We do multiple field maps within a session. We attempt to account for drift in field and or head motion by interpolating over time. Then we incorporate those field maps to correct the functional data. As you know, there's usual steps of correcting for slice time and motion, and of course using the field maps to correct for distortion, and we do all of this with a single interpolation of reduced blurring. And there's also some post-hoc homogenization of the EPI data having to do with the RF coil biases that is very typical depending on the coil that you're using. Okay, so that's just kind of a broad overview. Of course, there's a lot of details of how to do this and so forth. So just a smattering of additional images and movies. This is just a high-res T2 star EPI data against the T2 after the supposedly correct co-registration. There are, of course, artifacts in the EPI data, such as apparent dropout, so you don't want to confuse dropout for apparent scaling of the brain. There was an affine transformation being used here to determine this registration, so I think visual inspection of the quality of the registration is really important, especially for intermodality registrations where one of them may be corrupted by image artifacts, namely the EPI data. What's this next one? So this shows you a little bit more about the layers, right? So this is just lopping off the posterior third, somewhat obliquely part of the brain, and you can see the only difference between this and this, the top image and the bottom image, is just the layer sampling. So actually, whether you sample near the white matter or the peel surface, it does actually make a big difference. We're talking about 2 to 3 millimeters of sampling difference, and so the surfaces look different. This is just a movie showing, with pretty good T1 data, the automatic FreeSurfer segmentation with layer expansion, at least by eye at a gross level, looks pretty accurate. Of course, if you stop and squint, there are a lot of problems that still are present even after acquiring 9 T1s and averaging, which is a whole nother headache. But anyway, so this is part of our high-res processing, making these distinct cortical surfaces and sampling all the functional data onto these surfaces. Just a brief glimpse into the field map handling. So field maps are basically 2 separately acquired volumes differing in echo time, and you basically use the phase progression between these 2 echo time volumes to estimate the field strength. This is the magnitude, not the phase, of the field map scan, and here's the corresponding field map derived from the 2 different volumes with pseudo color to represent the field offset. Of course, you can. This is I don't know what resolution this is conducted at. Anyway, you can see you get a apparent field estimate everywhere, even when there's no proton signal. So it's important to regularize this, and so we use a specific statistical method to regularize this. It's a local linear regression where we're using the field map magnitude as a weight in this local regression process. I think this is important because if you use these field maps in a lot of these approaches, the quality of results is directly dependent on how good the field estimates are. And so this is an image showing that. So this is just before and after undistortion. We're not using any brain masking, which I think I see some people do, because the brain masking itself could be susceptible to problems. Anyway, so this is before and after distortion, and it's very hard to see here, but this is supposedly the more anatomically correct. This is the field map volume, and you could do we're not going to do it right here, but you could do a comparison that the distortion is in fact working well. Of course, how well it's working is very hard to know for sure. Okay, so moving on. One thing in the pre-processing routines we do is just to generate a lot of visualization. So this is actually the first. I like to do this for all my data sets. It's the first and last volume of each of our runs, and so our sessions are long, over up to an hour and a half. And so just this, and this is after pre-processing, so in a volumetric pre-processing sense. And so you want to see stability of your, motion-corrected slice, field map undistorted, and slice time corrected data. And so if you just eyeball these movies, we're looking for stability. It looks pretty stable. Of course, if you have data sets where there were problems, you will notice instabilities, and this will just give you a heads up as to something wrong in the session. Anyway, so this all comes for free in the pre-processing routines. I mean, it's not hard, but just having something that always gets run is important, I think. Let's see. This visualization, you've seen some of these, although the one on the left is new. But without getting into too much detail of what the one on the left is, it's basically a visualization of a one-dimensional profile of evoked amplitudes, bold amplitudes, in an fMRI data set where different colors correspond to different stimulus conditions or experimental conditions, where the width of the lines indicate measurement error, and we're just sampling a very little part of our high-resolution data set. So if I play these two movies against each other, you can kind of see a correspondence between where we sample, looking at this white line that's moving down posteriorly on the ventral aspect of the brain. This is actually the fusiform gyrus, so we're just sampling the high-resolution data at different posterior, anterior levels, just trying to see the effect on the data. As you can see, there's a lot of detail, and there's a lot of data to pour through. And yeah, so. Okay, next, yes?
So how do you make that? Like, is it like manually you set the points?
Yeah, currently actually the guy who made this, I don't know what he did, but presumably, yeah, you decide which part of the brain you want to look on. You click, and then maybe you define a range, like move from here to here, and then it'll give you these movies. Okay, moving on. I did mention co-registration, and I developed this thing ages ago. It's a pretty simple tool for registering volumes. And I guess a couple of the aspects that I think are important about it, it's very flexible. It doesn't even need brain data, right? It's just any two volumes. And in a lot of preparations, you don't have whole brain coverage. And so automated methods for aligning two things where one thing has very little data can be susceptible to, vastly incorrect solutions. And so having the ability to both manually adjust it as well as use automated tools, in the case that you have great data, maybe you want to determine the real optimal registration between two volumes, and to do that by eye is very difficult. So we want both the ability to do manual and automatic optimization, restricting the optimization to only parts of the volume that you care about, because in EPI data, again, there are a lot of artifacts. You might want to avoid the scalp or avoid dropout regions, so you can simply supply a spatial mask, different types of transformations, of course. And so here's a little example. There is a GUI, but it proceeds. You can proceed automatically. So on the left, you have the supposedly registered data. I'll play the movie in a second. And you have various, translation, rotation parameters, scaling, sharing, and various visualization manipulations. And so in this movie, So right now we're going to turn on the automatic optimizer. And so it's just based on MATLAB's built-in optimization routines where we're, in this case, changing the rigid body parameters. And you can see one volume. I guess one volume's the EPI data. That's the one that you can't see most of the time. And then the one that it lives on is the T2. So it's just doing an EPI to T2 alignment. And you can see the optimizer's progress and descending the error surface, trying to maximize the, I believe in this case, correlation between these two pixel intensities. So it's kind of fun to watch, but of course you don't have to do this. You can go off and, this is all automatic, so you just leave it running in the background. And it'll do its thing. Let me just speed it up, go on, after a while, it'll get closer to the right solution. Here we're gonna optimize scaling. You can kind of see kind of a stretching of this volume, although if you missed it, you missed it. I'll just start it back over at the beginning. Okay, so you'll see some stretching. There you go. So for many reasons, there may not be rigid body correspondence even between a same brain and its own brain. We could talk about that. So in this case, it's now optimizing the rigid scaling and shearing parameters. And then eventually, for this data set, it should look better. And this is basically at the end, where the EPI and T2 are in pretty good correspondence. Again, this is, of course, subjective. We don't know how good is good, and it's very hard to get quantitative metrics of, what is the spatial precision. But at least by eye, I'm confident to say that this is well below 0.5 millimeter in any direction. Okay, so next random topic, analyzePRF. So some of you may be familiar with this. So coming from the vision world, I guess, is where the term PRF comes from. It stands for population receptive field. And it's not actually a very vision specific thing. People are now doing this in the auditory domain. And in fact, I don't even think it's sensory specific. It's a very general idea that you want to fit a model that relates to things, in this case, stimulus and response. So we're talking about fMRI data, and here's the type of stimulus. So in the visual domain, we basically sample space being the visual field. So you can stimulate different parts of the visual field in whatever pattern you think is optimal. That's a whole nother discussion. In this case, we're just stimulating left and then going through the middle and stimulating the right. And so depending on the stimulation pattern, you may observe different responses from a given set of neurons or neural population as measured in fMRI. And we want to basically learn something about the preferred tuning of that neuron or set of neurons. And so this approach posits some sort of model of this, and the details don't matter other than to say that in this model we are attempting to fit parameters describing a simple two-dimensional Gaussian. So there's just a handful of parameters, and it's a fitting problem. I mean, we know the stimulus, we observe the response, the time series, the fMRI time series, and we just have to determine the optimal parameters in a least square sense. So it's not conceptually that difficult. Of course, the devils are in the details. And on basis of fitting these models, you can do things like map out topography. So in visual cortex, we get demarcations between different visual areas, traditionally based on retinotopic estimates, meaning estimates of their preferred position in the visual field. And so this is actually from connectome data way back when, where we used, I guess, connectome retinotopic data pushed through this type of model to derive these type of estimates. Again, pretty pictures if you don't know what this is, but it's basically topography of the back, the posterior aspects of the cortex. Moving on, I know this is a smorgasbord, but that was the point. So GLM denoise is a tool / technique / paper I did a couple years ago, having to do with dealing with noisy fMRI data. So as Olaf alluded to, fMRI data has a lot of problems, especially for connectivity. For example, head motion, in a sense, correlates noise across the brain. Physiological noise correlates activity across the brain, etc. So in the task domain, what's typical is to take your time series data and use a GLM of some sort to estimate evoked responses in each voxel. So kind of a univariate regression model. And it would be nice if we knew what the noise was, because then we could straightforwardly incorporate noise regressors into the GLM and attempt to get better estimates of these amplitudes, otherwise known as beta weights. And so this is not people there's flavors of this throughout the literature. And so just very briefly, I don't know how much of the details. So this is a regression model where we're just using variables to symbolize different things we know. So y is the time series. This is just a review of what a GLM is. We have the time series observed, the fMRI time series, and we know the experimental design, and there's typically an assumed time course of the HRF. And what we're trying to estimate are the amplitudes, symbolized by H here. And typically we know that we expect massive amounts of low frequency drift. So in this case, we incorporate that in the design matrix, in the experimental characterization. Here we separate that out from the design matrix. So that's very typical. And the key is, what are these global noise regressors? So, there are many approaches. One is to, use external physiological monitoring to try to sort of derive them from physiological data. In this particular technique, we use a data-driven approach, similar to ICA, but different in the details. And the basic idea is since initially you don't know what they are if you're trying to derive from the data, so we just fit our data set without any noise regressors, and so this is just a depiction of that. So we have just one slice. Color here is indicating good variance explained in a cross-validated sense and given our experiment. And you see there's plenty of signal, but there's plenty of voxels that don't have any signal at all according to this metric, and that's given by the complement of this map, which is basically you have water signal, but you have no experimentally related signal. So that's what we call the noise pool, and then we just do PCA. So PCA captures variance in a very succinct fashion. And then the question is, how many of the PCs are sufficient to describe most of the noise? And that, to me, it can only be determined empirically, so we use cross-validation to figure that out. So that's all the technique is, and typically you observe something like this where you get benefit from a couple, and then at some point you start overfitting. So that's all it is. Conceptually, I think it's simple. Code-wise, it is a little complicated, especially since there's a lot of visualization I also add, because I think visualization is important. Anyway, so that is the technique. And then moving on to the last, 7 of 7 is statistics and model fitting. So nothing to do necessarily with brain stuff, but I think statistics and doing analysis, I think analysis is a more general term. Doing analysis correctly I think is really important. So I guess I have done a bunch of simulations and statistical tutorials in the past. Why are they useful? Well, teaching, that's of course one goal. And of course, knowing that your code is correct. So this is beyond statistics. I mean, you code a complicated thing, there are inevitably bugs unless you're a really awesome programmer. And having small scale, well-defined checks or simulations I think is really important. So these are just slides from some statistical materials I generated for a class, and the idea is all of these come from simple simulations that I coded up to make pretty pictures, but they weren't just faked data. These were simulated data whereby we demonstrate various statistical concepts. You can check out this website if you're interested about that, which is coding. Coding's important. And there's a kind of the predecessor to the class was this statistics blog that I used to write on, but I haven't touched in a long time, where again we use code. So there's some code online you could run to generate various plots and that demonstrate various ideas and concepts. And I think they're cool. And what else? Oh, and then getting more about two-brain stuff. So in this paper, we used some sort of statistical approach to model these particular brain areas. The details don't matter other than to say that, well, we put code demonstrating how this all works. We make available the data so you can try your own model or try your own approach. And we have some relatively simple code snippets that take the data and implement this particular model and do cross-validation and so forth. And so you can check that out if you're interested in that. Oh, that was pretty quick, but it was 33 minutes. Okay, so just a summary of what you've seen, just in case any of this is interesting to you. Some automated brain surface visualization stuff, brain art, sort of going with number one. A preview of the kind of high-res pre-processing approach we take. This volume co-registration tool, which is pretty straightforward. This stimulus response or parametric model fitting applied fMRI data type code. Some GLM-oriented task fMRI denoising algorithm and code. and statistical simulations, which I think are nice and easy. And again, all of this is somehow talked about or alluded to or linked to from the lab website. So if you want to check that out, you can go there. And I'd just like to acknowledge on the visualization end of things, so these pretty movies and so forth, Keith was involved in developing this automated surface visualization code, and Ashed, who's a grad student at Stanford, did that movie where you see that little line moving across cortex and you get a nice visualization of the very detailed map of activity patterns on the left-hand side. And that is it.